you know, like the drop down boxes and stuff, it doesn't show on Steam, so I switched to screen cap, so you see everything on my screen. Anyway, so yesterday we got up to if statements. What else did we do yesterday? While loops. A few different variables we went through, right? We're actually halfway through this chapter, so today we're gonna finish this chapter, because I quickly scrolled through it and there's still quite a bit left, so I think it'll be long enough with all the coding in between. So we're just gonna finish this chapter today. So, composite assignment operators. I'm sure we'll find out what that means. Tell me if the music is too loud as well, by the way. If you can hear me over it. I guess you can. It seems like you can. Incrementing a variable, that is, adding 1 to it, is so common in programs that C++ provides a special syntax for it. For example, ++counter means counter equals counter +1. There are many other common ways of changing the value of a variable based on its current value. For example, we might like to add 7 to it, to subtract 9 or to multiply it by 2. Such operations are also supported directly by C++. For example, a plus equals 7 means a plus 7. A minus equals 9. B minus equals 9. Sorry, means b equals b minus 9. C asterisk equals 2 means c equals c asterisk 2. It's a weird way of writing that. Very weird way of writing that. In general, for any binary operator, opper a opper equals b means a equals a opper b. For starters, the rule gives us operators plus equals, minus equals, asterisk equals, / equals, and division equals. This provides a pleasantly compact notation that directly reflects our ideas. For example, in many application domains, the multiply equals and division equals are referred to as scaling. An example finding repeated words. We did this the other day, right? It's different, okay. Consider the example of detecting repeated adjacent words above. We could improve that by giving an idea of where the repeated words was in the sequence. A simple variation of that idea simply counts the words and outputs the count for the repeated word. So I guess we can go change this. We start our counter at 0. Each time we see a word, we increment that counter. ++ number of words. That way the first word becomes number 1, the next number 2, and so on. We could have accomplished the same by saying number of words plus equals 1, or even number of words equals number of words plus 1. But ++ number of words is shorter and expresses the idea of incrementing directly. Note how similar the program is to the one from which we did yesterday. Obviously we just took the program from 3.5.1 and modified it a bit. Yeah, repeated words, yeah. It a bit to serve our new purpose. That's a very common technique. When we need to solve a problem, we look for a similar problem and use a solution for that with suitable modifications. Don't start from scratch unless you really have to. Using a previous version of a program as a base for modification often saves a lot of time, and we benefit from much of the effort that went into the original program. So let's go do that then. Let's go change it, right? Might as well get straight into it. So 2 repeated words. Please. Why isn't it showing? File view. No view. How do I turn this back on? I kind of... Let's go back to the start page. Okay, it just doesn't show up. Let's, it should be here somewhere, right? There we go. It didn't. Woo! Alright. So this is where we were. Let me scroll to this. I'm gonna have to do that. There we go. Okay, so what's changed? We've still got previous and current. Take away the overlay. It's only at the top. You don't need to see that. Right, well, we still got this. There's a new variable he's made. So int number of words. That's right, because we need to count number of words. And we need to set it to 0. String previous, string current. While Cn reads current. Okay, so this has changed completely. So we're not telling them what the repeated word is anymore. We're doing word number. Word number. Number of words. Oops. There we go. That's what I meant to do. Number of words. And he's done this. Spell it right. Repeat it. Yeah, sorry. I live right next to the road. Sorry. Repeated, and this is and then current. Yep, that's the one. And then and then this. So for the new line. And then previous equals current. That's everything, right? Except he's put it. He's done it on a new line, so it's easier to read, I guess. There we go. Yeah. So he's changed it. So see how it is the word number and then number of words, which is the one we made up here. Ah, we missed. While, or I missed rather. Plus plus. Plus plus number of words. I can't now, Heather, because all the songs mute the VOD, and then when I put it onto YouTube, it gives me loads of copyright claims. So whilst we're doing this, I can't. This music I've got on now is like stream-friendly music. It's Monstercat, so nothing happens with this music. That's why I've got it on. Sorry, no fun allowed. Yeah, sorry. But when I'm playing games, I don't care. Just whilst I'm doing this. Yeah, I don't think the copyright claims actually do much at the moment, but like I got 3 different copyright claims on the one video last on the chapter 2 one that we did yesterday's. I can show you actually. If I open my emails, I will open it on the other screen so you don't see them all first. Here we go. So you can see my emails now. That's 1 for whatever Sorry was. Oh, this is chapter 1, sorry. So Sorry got 3. And then Beep Beep by Mashik Remix was a copyright claim. And then Baby, which I guess was the Justin Bieber you put on that day. That's a copyright claim as well. Yeah, on YouTube, yeah. It just means they're gonna show adverts and take money if anybody watches them, which nobody watches them, but but they might do in the future. Who knows? Did you get this working, by the way? They'll never take the channel down, they just put adverts on and stuff, or make you delete the video if it's super serious. I'd never have to pay or anything like that, it doesn't work like that. Anyway, did we get this working? I didn't even try mine. Helps if you try it, right? There were build errors, so no. Oh, okay. I forgot to put the yeah. Douche. Yours is super slow. Let's move that over here so you can still see what. Nice. The cat jumped over the moon because he capital is stupid. Stupid. Hey, that's quite clever. It tells you where the word is and everything. I feel so clever right now. So you got it working first time as well? Just don't really work. Why? Did you... I forgot, if you followed me, I forgot, if you didn't catch me adding it in, this plus number of words. The dog ate the big ass bone. The dog ate the big ass bony bone. There you go. So yeah, if you followed me, I forgot to put that in if that's what's not working on yours. Nice. Nice. You know, Heather, this would be much easier if you spoke on like Discord or something. Don't tell me which words. Alright, I'll let you try and figure it out then. It's the best way. I only have TeamSpeak. Do you have a TeamSpeak server? Are they free? Let's go find TeamSpeak. TeamSpeak is like so 90s. Nobody uses TeamSpeak anymore. Windows 64-bit. Nobody program. I think that's right. Still called, yeah, okay. I do not want overlay. I hate that overwolf shit. Okay, if I go back out one. Maybe let's just show everybody the password, right? Oh shit, I'm actually gonna have to change this shit. Right, let's open that again. And hope it opens on the other screen. It's not even opening now. Oh, there we go, it's because it's already open. Oh shit. I can go as well. How the fuck do I open this shit? Please. I actually have no idea how to use this. Alright, it's time to Google. I guess time to Google. Oh, do you have to pay for this shit? Oh, okay. Does not require a license. Okay. I mean, how do I connect to this server then? I'm trying to figure out how to make a server. Oh, it's like the same as hosting the Minecraft server when I did that. Whatever, I'll do it like some other time. Carry on with this shit. I'll do it for like tomorrow or something. Yeah, I'll do it tomorrow. Let's just carry on with this. Because I need to like go set up port forwarding and stuff. And I don't want to do that shit on stream, so... We'll stick to talking over Steam chat for today. We've got this working, right? Did you get your count working? For what? You said it didn't count. Did you get this the program working for the counting the words and telling you which word it is? You said you were gonna do it. Gonna try and fix it. Cool. That's a good cup of tea. Nice. Virtual high five. So if everything works both ends, I'll just do it again for... Or not. Or not. The brown little fucktard was doing tardy ass things like they do. Repeated every word. Sounds like you've got like one of the variables in the wrong place on this if bit. Sounds like it, but hard to tell without seeing, but you can probably figure it out. You seem to have this shit down. It's like a little cha-cha. Oh, let's move this out of the way as well. That helps. Do. It works not. Oh no. Oh, okay. I thought you were like super stuck then. That's cool. So just to go over it, well, let me close this. Just to go over it, we added the number of words. We did the plus plus to increment it by 1 every time it reads into current. So while cin is going into current, it does this. So every time current gets overwritten, it does everything in this bit. So it adds 1 to the number of words, and then it checks to see if the previous word is equal to the current word, and if it is, it writes out the word number. Number of words, writes out that number of words that it's currently on, and then the current word to say which word it was, and then sets that current word to the previous into this previous, and then returns back to the beginning, it goes back to the beginning for the while loop, and does the same again for the next few words until it gets another repeat one. So, just to go through the code so I understand it a bit better. Back to the book, I guess. Let's carry on. Back to the book. Names. So we're on names. Oops, stop highlighting shit because it comes up. We name our variables so that we can remember them and refer to them from other parts of the program. What can be a name in C++? In a C++ program, a name starts with a letter and contains only letters, digits and underscores. For example, x, number of elements, Fourier transform, z2, polygon. The following are not names. 2x, a name must start with a letter. Time, dollars to dollar market. Dollar is not a letter, digit or underscore. Start menus. Space is not a letter, digit or underscore. When we say not names, we mean that a C++ compiler will not accept them as names. If you read system code or machine-generated code, you might see names starting with the underscore, such as underscore foo. Never write those yourself. Such names are reserved for implementation and system entities. By avoiding leading underscores, you will never find your names clashing with some name that the implementation generated. Names are case sensitive, that is, uppercase and lowercase letters are distinct, so X and X are different names. This little program has at least 4 errors. Includes standard lib facilities. Main is in capital M, so that's not a right thing. String is in capital, so it doesn't work. S equals goodbye cruel world. C out, the capital O wouldn't work, and capital S isn't what he made. Yeah. And the capital S wouldn't work because he made it a small s if the string was a normal string. It is usually not a good idea to define names that differ only in the case of a character, such as 1 and 1. That will not confuse a compiler, but it can easily confuse a programmer. Try this. Compile the Goodbye Cruel World program and examine the error messages. Did the compiler find all the errors? What did it suggest as the problems? Did the compiler get confused and diagnose more than 4 errors? Remove the errors one by one, starting with the lexically first, and see how the error messages change and improve. Should we do that, or should we just skip it, or do you want to go through the errors? The C++ language. I will wait for your reply. Do you want to make this program with all the errors and go through the errors? Or are you happy to carry on? Oops. I'll carry on. We already spotted all the errors as we went through it anyway, so... the C++ language reserves many, about 85 names, as keywords. We list them in 3.1. You can't use those to name your variable types, functions, etc. For example, int if equals 7, error if is a keyword. You can use names... Let me turn down my music in my ear. There we go. You can use names of facilities in the standard library, such as string, but you shouldn't. Reuse of such a common name will cause trouble if you should ever want to use the standard library. Int string equals 7. This will lead to trouble. When you choose names for your variables, functions, types, etc., choose meaningful names, that is, choose names that will help people understand your program. Even you will have problems understanding what your program is supposed to do if you have littered it with variables with easy to type names like x1, x2, s3, tab p7. Abbreviations and acronyms can confuse people, so use them sparingly. These acronyms were obvious to us when we wrote them, but we expect you'll have trouble with at least one. MTBF, TLA, MYW, MBV. We expect that in a few months we'll also have trouble with at least one. Short names such as X and I are meaningful when used conventionally, that is, X should be a local variable or a parameter, and I should be a loop index. Don't use overly long names, they are hard to type, make lines so long that they don't fit on a screen, and are hard to read quickly. These are probably okay. Partial sum, element count, stable partition. These are probably too long. The number of elements, remaining free slots in symbol table. Our house style is to use underscores to separate words in an identifier such as element count, rather than alternatives such as element count and element count. We never use names with all capital letters such as all capital letters, because that's conventionally reserved for macros. I was taught to do it like this when I was taught the first time, so this underscore thing is hard for me to remember. I was taught to do, you start with a lowercase, and then if you start another word, you start it with a capital. So I guess you could use either, but which we avoid. We use an initial capital letter for types we define, such as square and graph. The C++ language and standard library don't use the initial capital letter style, so it's int rather than capital I with int, and string rather than string with a capital. Thus, our convention helps to minimize confusion between our types and the standard ones. Avoid names that are easy to mistype, misread, or confuse. For example, name with a capital S, foo, F1, FI, well, I think that's an FL. The characters 0, O, and O, uppercase O, 1, I, and lowercase l, are particularly prone to cause trouble. F1, FL, and FI are all, types and objects. For Alt and F4. That's the answer to everything. So it's types and objects. The notion of type is central to C++, and most other programming languages. Let's take a closer and slightly more technical look at types, specifically at the types of objects in which we store our data during computation. It'll save time in the long run, and it may save you some confusion. A type defines a set of possible values and a set of operations for an object. Yeah. Alt F4, that's how you make games, right? Yeah. No. An object is some memory that holds a value of a given type. A value is a set of bits in memory interpreted according to type. A variable is a named object. A declaration is a statement that gives a name to an object. A definition is a declaration that sets aside memory for an object. Sorry, my mouth is really dry. Hold on. And I have like no drink left now. Informally, we think of an object as a box into which we can put values of a given type. An int box can hold integers such as 7, 42 and minus 399. A string box can hold characters, string values such as interoperability, tokens, and all those symbols. And old MacDonald had a farm, whatever. Graphically, we can think of it like this. If you've learned by images, int a equals 7 is a into a box of 7, yada 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 yada. Mad cow. The representation of a string is a bit more complicated than that of an int, because string keeps track of the number of characters it holds. Note that a double stores a number, whereas a string stores characters. For example, x stores the number 1.2, whereas s2 stores the three characters 1, point, and 2. The quotes for character and string literals are not stored. Every int is the same size, that is, the compiler sets aside the same fixed amount of memory for each int. On a typical desktop computer, that amount is 4 bytes, 32 bits. Similarly, bools, chars, and doubles are fixed size. You'll typically find that a desktop computer uses a byte, 8 bits for a bool, or a char, and 8 bytes for a double. Excuse me. Note that different types of objects take up different amounts of space. In particular, a char takes up less space than an int, and string differs from double, int, and char. In that different strings can take up different amounts of space. The meaning of bits in memory is completely dependent on the type used to access it. Think of it this way. Computer memory doesn't know about our types, it's just memory. The bits of memory get meaning only when we decide how that memory is to be interpreted. This is similar to what we do every day when we use numbers. What does 12.5 mean? We don't know. It could be $12.5 or 12.5 centimeters or 12.5 gallons. Only when we supply the units does the notation 12.5 mean anything. For example, the very same bits of memory that represent the value 120 when looked upon as int would be x when looked upon as a char. If looked as a string, it wouldn't make sense at all, and would become a runtime error. If we try to use it, we can illustrate this graphically like this, using 1 and 0 to indicate the value of bits in memory. 0 0 0 0 0 0 0 0 0 yada 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 0 1 1 1 1 1 0 0 0 0. I guess you need to know binary to understand that. I don't know if it's going to go over it, but this is like a byte here. So this is a byte. Every 4, I think, is a byte. Or is it 8? 8. Yeah, every 8 is a byte. That's a byte. That's a byte. So that's 4 bytes right there. And it's really hard to explain with that right now. It's not going over it, so this is setting. A bit is a unit of computer memory that can hold. This is the setting of the bits of an area of memory that could be read as an int 120 or as char, looking at the rightmost 8 bits only. A bit is a unit of computer memory that holds a value of 0 or 1. For the meaning of binary numbers, see 2.11. Yeah, so it's a bit and a byte. It's hard to explain how binary works. So it starts with, this 0 here, the very first one, is a, I'll write it out actually. I can open Notepad. Notepad. Okay. You can see this on stream, right? That's big enough. Oh, you can't see it through the, I need to switch to that one. There we go, there. Okay, so it's 4, 5, 6, 7, 8. So the way it works is this first 0 is that's nothing, right? So, but that would equal 2 if it was that. In fact, I'll write it underneath. So it's 2. Okay, so that's 8. So 2, 4, 8, 16, 32, 64, what's 128, and 2, 4, 2, 5, 6, yeah, 2, 5, 6. So that's like each one, so like, I think that's right. This way? Oh. This way? I think that's wrong though. I think it might start with 1. So 1, 2, 4. It must do. 1, 2, 4, 8, 16, 32, 32, 64, 128. There we go. So that's what they each stand for. So you out of that you can make any number you want. So if you were to if you wanted do an easy one, if you wanted 17, you would do that would be 1 0 0 0 1 0 0 0. So that's the number 17 in binary, right? So we've got 1 on this one, so we've turned that one on. which makes 1. And then 0, because we don't want any 2s, we don't want any 4s, we don't want any 8s. So we've got 3 zeros, and then we've turned this one on, 1, which makes 16, and plus the 1 is 17. And then 32, 64, 128. And this is why everything in computers is in this format, right? So you always have like 128 kilobytes or something, and like when your memory says when your memory says like you've got a terabyte of memory, you haven't. You've got like 128 gigabytes or whatever, or 1,280 gigabytes. So you've actually got a little bit more than what it says, because it doesn't work like that. Like computers don't read anything in absolutes. So like if that's a byte, then the next byte would be like say you wanted to make 560 or something like that. I can't do that math. Let's make it easier. Let's do 100. So you do 64 plus 32 is 6, 9. I think that's not enough. Alright, I'll make it really easy. That's not enough. So 130. So if we go for 130, we'd need 2 bytes, right? So we'd have to go 0, 0, 0, 0, 3, 4, 5, 6, 7, and then the 8th would be on 1. So that's 128. But we need more than that, so we could actually do that with 1 byte. Actually, that's still not big enough, because we could just add the 2. We could just add the 1, 1. That would be 131. It's still not big enough. Let me get a calculator. I can't do math. 128 plus. There we go. So if we wanted 200 and make sure that's right. Yeah. Okay, so if we wanted 256, which is another very popular number, you'd have to have 2 bytes, so it'd be everything would be on 1 on this one, so 1, 2, 3, 4, 5, 6, 7, 8, and then because that's the maximum number you could make, which is 255, you'd have to go 1, 2, 3, 4, 5, 6, 7, 8. So now you've got 2 bytes of information because you've gone 1 number over. So just in 1 byte you can have 255, I think. Yeah. So when we're assigning these int numbers, and it says in the book that we've got 4 of these things, that means it can hold up to 255 times 4. So it can only hold up to 1020. It can go higher than that, but it'll just reserve more memory. But that's how that works. It's a very, very shoddy and quick lesson on binary. How binary works. And how you make numbers with binary. Don't save, we don't need that. Yeah, there you. Anyway, let's carry on. Alt_var01, type safety. Every object is given a type when it is defined. A program or a part of a program is type safe when objects are used only according to the rules for their type. Unfortunately, there are ways of doing operations that are not type safe. For example, using variable before it has been initialized is not considered type safe. Int main $x. We forgot to initialize. We didn't tell it what x is. The value of x is undefined. Yep. $y equals x. The value of y is undefined. Yep. We haven't even told it what y is. The meaning of plus and the value of z are undefined. Yeah. Because we don't know what x is, or y or anything. So, an implementation is even allowed to give a hardware error when the uninitialized x is used. Always initialize your variables. There are very few exceptions to this rule, such as the variable we immediately use as the target of an input operation. But always to initialize is a good habit that will save you a lot of grief. Complete type safety is the ideal and therefore the general rule of the language. Unfortunately, a C++ compiler cannot guarantee complete type safety, but we can avoid type safety violations through a combination of good coding practice and runtime checks. The ideal is never to use language features that the compiler cannot prove to be safe. Static type safety, unfortunately, that's too restrictive for most interesting uses of programming. The obvious fallback, that the compiler implicitly generates code that checks for type safety violations and catches all of them, is beyond C++. When we decide to do things that are unsafe, we must do some checking ourselves. We'll point out such cases as we get to them. The ideal of type safety is incredibly important when writing code. That's why we spend time on it this early in the book. Please note the pitfalls and avoid them. Excuse me. Safe conversions. In 3.4 we saw that we couldn't directly add chars or compare a double to an int. However, C++ provides an indirect way to do both. When needed, a char is converted to an int and an int is converted to a double. For example, char c equals x, int I1 equals c, int I2 equals x. Okay. Here both I1 and I2 get the value 120, which is the integer value of the character x. In most popular 8-bit character set, ASCII, this is a simple and safe way of getting the numeric representation of a character. We call this char to int conversion. Conversion safe because no information is lost. That is, we can copy the resulting int back into a char and get the original value. Click here to view code image. I don't want to do that. Char c2 equals I1, cout c, space, show I1, space, show c2, space. This will print 120. Oops. In this sense, that a value is always converted to an equal value, or for doubles, to the best approximation of an equal value. These conversions are safe. Bool to char is safe, bool to int, bool to double, char to int, char to double, int to double. The most useful conversion is int to double because it allows us to mix ints and doubles in expressions. Double d1 equals 2.3, double d2 equals d plus 1 plus 2. If d1 is less than 0, write to screen, d1 is negative. 2 is converted to 2.0 before adding. I see. So it changes it automatically to 2.0 rather than 2. For a really large int, we can, for some computers, suffer a loss of precision when converting to double. This is a rare problem. Oops. Safe conversions are usually a boon to the programmer and simplify writing code. Unfortunately, C++ also allows for implicit unsafe conversions. By unsafe, we mean that a value can be implicitly turned into a value of another type that does not equal the original value. For example, int main, int a equals 20,000, char c equals a, int b equals c. If a does not equal b, cout, try to squeeze a large int into a small char. Cout, oops, a does not equal b, else, we haven't gotten across else yet, but else is, else cout, well, we have a large characters. Else is like, if, I presume it's going to go through it. It does not mention it. So else is like, in the if statements we've wrote, this if bit is, you know what, I just realised we're on the wrong. This if bit is, what it's looking for. So if a does not equal b, it will do this, but just write the oops. A does not equal b, a new line. And then this else is, if this isn't true, then it will do this. It's just adding like a backup thing, so like in case there's an error or something. So if it's not, if this isn't true, then it will do this no matter what. Whereas the other if statements have been, it will just check if it is and then do it. Such conversions are also called narrowing conversions because they put a value into an object that may be too small, narrow, to hold it. Unfortunately, few compilers warn about the unsafe initialization of the char with an int. The problem is that an int is typically much larger than a char, so that it can, and in this case does, hold an int value that cannot be represented by a char. Try it to see what value b gets on your machine. 32 is a common result. Better still, experiment. Let's do it. The while statement that we used to allow many values to be tried will be explained. Okay, let's do it. So I'm going to need to press this one for this. So let's do save this. Oh, let's go back to 2. There we go. Save. Close. File. New project. Right, let's call it conversions and char values. Oops. Do the usual include. Okay. So double D. That's what we would like to see. There we go. Double D. That was terrible. Double while loop again. So while read the screen, read the input, and put it into D. Curly braces. And while that's happening, int I equals D. Make it a character. Character C equals I. Int I2 equals the character. Wait, why is that gone? Oh. There we go. Int I2 equals the character. Helps if you end your lines. And then we write cout right to the screen D is equal to D is equal to write out D. We'll make it readable as well. Write out space I is equal to and write out I, and then write out I2 is equal to, and write out I2. Oh, forgot the space here. Chart. Oh, this one's a function. Chart. C. So get the character and then show it. \n and this quote, new line, and that's it. That should be it. So and then we make our variables here, and then we're putting that character into D as we write it, and then D. And then we print out D, we print out I, which should equal D. And then we print out I2, which should be the same, right? C, I. So let's try it. Let's write it here. Keep window open. Oops. Keep window open. Oh, I guess it's just erroring. Ah, there we go. Just numbers. So yeah, 1111. The character though, it doesn't know. That's weird. So how do you reckon we can do 1, 2, 3, 4? It doesn't know the characters. I think it's using ASCII, so ASCII would be like 0153 is like, yeah, there we go. Yeah, I think this one's like copyright or something. No. 0179. One of them's like copyright. 0153. No. 0351. 0159. 0951. God damn it! I used to know this shit. Whatever. Whatever, we've got it though. It knows. Yeah. Oh, that's weird though. It comes out I2 is 75. 587, 587. Because that's the character number. So that character holds the value of 75, 39. Whereas the integer that we put in is the same. Did you get it to work? I'm sure one of these was... You have to go? Alright. Let's just quickly try and finish some of this little bit we're on then. Oops, no, that's the one I want. Yeah, finish to the next point. The while statement will be explained, that's what we just read. You'll find that many input values produce unreasonable results. Basically, we are trying to put a gallon into a pint pot, about 4 litres into a 500 milliliter glass. All of the conversions, double to int, double to char, double to bool, int to char, int to bool, char to bool, are accepted by the compiler. Even though they are unsafe. They are unsafe in the sense that the value stored might differ from the value assigned. Why can this be a problem? Because often we don't suspect that an unsafe conversion is taking place. Consider double x equals 2.7, lots of code, int y equals x, y becomes 2. Yeah. By the time we define y, we may have forgotten that x was a double. Or we may have temporarily forgotten that double to int conversion truncates, always rounds down towards 0, rather than using the conventional 4-5 rounding. What happens is perfectly predictable, but there is nothing in the int y equals x to remind us that information, the 0.7, is thrown away. Conversions from int to char don't have problems with truncation. Neither int nor char can represent a fraction of an integer. However, a char can hold only very small integer values on a PC. A char is 1 byte, whereas an int is 4 bytes. Yeah, there you go, 1 byte, 4 bytes. So we can't put a large number such as 1000 into a char without loss of information. The value is narrowed. For example, int a equals 1000, char b equals a, b becomes minus 24 on some machines. Not all int values have char equivalents, and the exact range of char values depends on the particular implementation on a PC. The range of char values is minus 128 of 127, but only 0 to 127 can be used portably because not every computer is a PC, and different computers have different ranges for their char values, such as 0 to 255. Why do people accept the problem of narrowing conversions? The major reason is history. C++ inherited narrowing conversions from its ancestor language C, so from day one of C++ there existed much code that depended on the narrowing conversions. Also, many such conversions don't actually cause problems because the values involved happen to be in range, and many programmers object to compilers telling them what to do. In particular, the problems with unsafe conversions are often manageable in small programs and for experienced programmers. They can be a source of errors in large programs, though, and significant cause of problems for novice programmers. However, compilers can warn about narrowing conversions, and many do. C++11 introduced an initialization notation that outlaws narrowing conversions. For example, we could and should rewrite the troublesome examples above using a list notation rather than equals notation. Double x 2.7 is okay. Int y x error double int might narrow. Int a is okay. Char b a error int char might narrow. I see. So instead of equals, you put it in the curly braces. Did not know you could do that. When the initializer is an integer literal, the compiler can check the actual value and accept values that do not imply narrowing. Click here to view code. Don't need to see it. So what should you do if you think that a conversion might lead to a bad value? Use initializers to avoid accidents, and when you want to conversion, check the value before assigning, as we did in the first example. In this section, see 5.6.4 and 7.5 for a simplified way of doing such checking. The curly braces list-based notation is known as universal and uniform initialization, and we will see much more of that later on. A drill, you have to go there, right? After each step. I think this is the end of the chapter as well. Review, terms, exercises, PostScript, yeah. So there's a big drill, lots of exercises, a few terms to go over. So I guess we can start with a drill tomorrow or something, and then carry on with chapter 3 or chapter 4 as it is in the book, but we've skipped the first introduction chapter because it's a massive introduction. But yeah, our third chapter. So I guess we'll stop there for the coding at least.